Hey guys, what's going on? Little bonus video for you. Bonus action, bonus time. Oh yeah. Black background, bonus video. Let's do it. I'm talking about graphs. Graphs are really important. Graphs are your friend. You need to understand how to manipulate graphs, how to interpret graphs, how to draw graphs, how to, do all the things with the graphs, okay? Because you're going to see a lot of them on the AP exam. You're going to see some tomorrow on the free response question. And then, just in life in general, it's just good to understand how to use graphs. They're useful tools. So, real quick recap on how some of the basics of graphs. You probably already know, but just go real fast and we'll hit up some new stuff here that is going to help you for tomorrow and in the future. Remember that, when we were talking about graphs, there's always two things we want to look at, right? I'm going to give you a position versus time graph real quick here. Basic graph. Position versus time. Always two things we want to look at. Slope, of course, and area under the curve of any graph, okay? Slope is always the rise over the run. And in this graph, it's the change in x, right? How much the x changes, how much it rises, divided by its delta t, how much the x-axis changes. Now, whenever you get a graph like, or any graph really, and you think about the slope, you think about area under the curve, and you think about, okay, how can this be useful to me? What is the slope going to tell me and all that stuff? Go back to your formulas for these two quantities. What are the quantities on the axes are? Go back and think, okay, what formulas contained those quantities? Of course, for these two, we had x equals vt. And there were more, but I'm not going to write them right now because I don't feel like it. And then, okay, well, if we rearrange this equation, what if we divided by t? Right, and these t's cancel like that. And then what do we end up with? We end up with x over t equals velocity. So, what does the slope of a position or displacement time graph tell us? It tells us velocity. We know that, right? We know that from memory at this point, right? And maybe you were wondering, or maybe you forgot why, because we haven't talked about graphs in a long time. Well, remember, this is why, right? It has to do, you go back to the equation. They all kind of interconnect with each other. Because the change in position divided by the change in time is the slope of the graph, that matches up with the equation, x equals vt. If we rearrange it to look like slope, or x over t, that's the same thing as slope, right? Change in x over change in t equals velocity. This is why the slope of a position time graph equals velocity. What about area under the curve? Well, area under the curve is always going to be base times height, right? In this class, we're not going to do integrals, so we're only taking triangle shapes and rectangle shapes. So we're always going to deal with area under the curve is going to be base times the height. If it's a triangle, it'll be divided by 2, but it's always base times height, whether or not we divide by 2. What's the base here? The base is time, and the height is x, so x times time. Now remember, we had our equation over here, x equals vt. Now can we rearrange that so it's x times t equals something? Well, we can. I guess we could do times t both sides. And then we get xt equals vt squared. And that doesn't really help us with anything, right? It doesn't really tell us anything useful. So it doesn't give us velocity. It gives us velocity times t squared. We don't really use x times t for anything. Oh, I just sneezed all over my fancy new graphic tablet. No big deal. So if you think back to class for a minute, have we ever discussed what the area under the curve of a displacement time graph is? We never have, right? Because no matter how you rearrange this, it doesn't really give us anything all that useful. X times t, or the base times the height. It just doesn't really, it's not useful for us, so we don't really mess around with it. We don't really care about area under the curve of that kind of graph. Well, you go to a velocity time graph, though. Velocity time graph is useful. Define the area under the curve, velocity time. Of course, you already know, right? The velocity time graph. You find the area under the curve, and it gives us displacement. Maybe you ask yourself, well, why was that again? I forgot. Well, okay, it's x equals vt is our equation we're going to use here. All right. And in this part of the graph, you find the area under it. It has a triangle, and this one's a rectangle, and you add the areas up. Okay, well, remember what the areas are, right? Base times height, or velocity times time. Velocity times time. There they are. When you multiply velocity times time, what do you get? You get x. That's displacement, right? That's the change in position. This is why the slope, or sorry, not the slope, area under the curve of a velocity time graph equals displacement. Right? It goes back to the formula. What else do we know with v times t? Well, we also know that acceleration equals the change in velocity, change in velocity over the change in time. What's the slope? What is the slope here, right? The slope is the rise over the run. The change in v over the change in t. That equals acceleration. This is why the slope of a velocity time graph equals acceleration, right? We've got to be familiar with this. We have to be able to know this, pretty quickly. Okay. Now let's go to something a little more complicated, a little more interesting. Okay. Let's say we get a graph or a problem, and it gives us a kinetic energy of something, and it gives us a velocity of something. And it says, okay, I want to know the mass of this object. What's the mass of it? And in a problem, they might give you a bunch of numbers. Maybe it's 100, and then it's 352, and then it's 578. I don't know. I'm making the numbers up, right? It gives you a bunch of numbers, right? And then at the same point, it gives you the velocity, right? Maybe the velocity is 10, and then it's 22, and then it's 31. I don't know. Again, whatever, right? And they give you a bunch of numbers. Now you could take this velocity here and this kinetic energy there, and plug it into our kinetic energy formula, right? You might think, yeah, why don't we just do that? However, in the real world, data fluctuates, right? It's changing. No instrument is perfect. And so the measurement at this instant won't precisely kind of line up, so to speak, with a measurement at the next instant, right? So instead what we do when we get data like this in the real world, and what you'll be asked to do on an AP question, most very likely, is to find the mass of the object, or maybe some other quantity, using a graph. All right, so let me show you how we can do this. Well, let's look at our formula back here. All right, k equals 1/2 mv squared. Well, we have k and v, and we want to find m. So what if we rearrange the equation so that it equals, or so that it's equals m? Let's rearrange it. We want to find m, so let's rearrange it so that it equals m. Well, how do we do that? Okay, well, first we got to do times 2, because we want to cancel that 1/2, right? So times 2 both sides. The half and the 2 cancel out. Okay, now we have 2k equals mv squared. We want to divide by v squared, right? Divide by v squared both sides. V squared is cancel this side. So we have 2k over v squared equals m. Oh, cool. Well, there you go, right? Now I have equal to m. And so, well, how does that help me with a graph? If I have to make a graph, how is that going to help me? Okay, think about it for a minute, right? Since a graph, what if we plotted the rise over the run? We don't have to make the rise a single variable like x or v. It can be 2k. We can take this k and times 2 every one of these values, times 2, and get whatever the new number is, right? And then whatever that number is, it'll be 200. Whatever that number is, plot that. And we can take this number and square each one of these values, right? Square all of them. And then plot that value on the axis. Rise is 2k. Let's plot, I'm going to get a little line here just to separate that out. 2k on the y-axis, v squared on the x-axis. And then we plot the points. Maybe it's there, wherever they are. We don't really care about that, what the line looks like. But whatever the line is, the slope would equal the mass, right? Because we already proved it right here. Right? So we would find, okay, what's the rise? What's the rise? Well, that's the change in 2k. It's 2k is a rise. Divided by v squared. That's the run. Right? And we set them, we arrange the equation like this way, we plot the points that way, and that'll give us m. Now, I will warn you that this particular example doesn't actually work because it wouldn't be linear. But my point is that whenever you get a problem that gives you data or whatever the problem is, right? Think about the equation of that thing, of those quantities, okay? There might be more than one equation. You might have to play around with it a little bit. You might have to do some substitution, okay? You might have to take, MGH at the top of a hill and the kinetic energy 1/2 mv squared at the bottom of the hill, right? You know how we've been talking about how energy is transformed, and say, okay, well, m's will cancel, and then if maybe I'm trying to find h, I don't know, So I do divided by, if I divide by g, I get 1/2 v squared over g equals h, right? Well, if I could plot a graph where on the y-axis it was 1/2 v squared, and on the x-axis it was g, okay, and then get a line, and the slope of that line would be the height, right? Because we proved it here. We make this the rise, make this the run. This could work for anything, okay? I'm just giving you examples, okay, of how we could use this technique, okay? So I'll tell you right now, tomorrow on the first free response question, you're gonna have to do something very, very similar to this. All right. It won't be quite this messy, I don't think. But do something like this. All right. So it got a little messy here at the end. Hope you followed that. If you have any questions, message me, email me, or send me a message on Remind. And good luck tomorrow, and I'll see you then. All right. Bye bye.